we are try to discuss a few simple questions, and I will try to remind you the idea of this one. So we go for a few questions for chapter 1. So for example, problem for 1.1. So a sphere 1.4 centimeter in diameter is placed in free stream 18 meter per second, 20 degrees Celsius and 1 atm. Compute the diameter Reynolds number of the sphere if the fluid is air, water and hydrogen. So here again, I think you already know the equation for Reynolds number, rho Vd over mu. But as a master student, you must know that actually there are three conditions for Reynolds numbers. Okay, one is called flow in pipe. So the two is the flow around bluff body, flow around bluff body. I'm sorry. Flow around bluff body, and the third one is actually open channel. So as a master student, you must make sure that you know the situation before you use any equation, because sometimes it will give you different equation and different limit. And then I just bring you the Reynolds number because this is the most common dimensionless number for fluid mechanics. There is a lot of dimensionless number. I hope you could study for that, because if you do fluid mechanics research, the dimensionless number is important. But you must use dimensionless number based on the situation. Okay, for example, if you want to reuse Reynolds, first you need to understand that Reynolds number will give you information about laminar and turbulent, but it's depend on the situation, the flow in pipe or bluff body or open channel. So for example, what we have here is about the flow in pipe. So the equation is something like rho Vd over mu. And then if you have the flow around bluff body, so it's closely related with the idea of boundary layer. So the Reynolds number is rho VL over mu. So and then for the open channel, the equation is will become rho V RH. So RH means hydraulic radius over mu. So means the equation is slightly different. So you need to really careful. So and then about the limits, you know, Reynolds number show you the idea of laminar and turbulent. So for flow in pipe, so there is 2000 and 4000. So mean if the velocity is less than 2000, so means that it is laminar. If the velocity, if the Reynolds numbers is more than 4000, it is turbulent. So this is for flow in pipe. So and then for bluff body, so the transition or the boundary between laminar and turbulent will occur at 5 times 10 to the 5. So quite big numbers compared to the flow in pipe, but in open channel, so the number is between 500 and 2000. If the Reynolds number is less than 500, it is laminar. If it is more than 2000, it is turbulent. So means that please be careful, because the equation is everywhere in the textbooks, but the spirit of master student, you need to use that very carefully. You could choose the right equation for the right situation and so on and so forth. Okay. So and then this is the calculation. So you could write the rho Vd, you will substitute everything. So you will get the value of 60,000 in air. In water is 250,000. So and then in hydrogen it is around 2,300 Reynolds number. So bear in mind that it is Reynolds number didn't have any units, so it's just a dimensionless number. Okay, so we go for the new ideas, which is Okay, for air and water, it is okay for us to use the common velocity of density, which is 1.2, 900, and for hydrogen, so we just use 0.0838. Okay, but what I want to say here is, so the question is, okay, so the problem is about the viscosity here. So the density, rho is equal to kilogram over meter cube, means the mass over volume. So because density has parameter for mass, so the conservation of mass will come in, so means that it is not easy for that gas and liquid to change their density. Okay, so however, the value of mu here, so mu is the kinematic viscosity, it's a little bit fragile value, means that it can be easy to change because it is affected with temperature and pressure. So let's say we take example of hydrogen. So we know that hydrogen has molecular weight of 2.016. So that we could calculate the constant number here as 8,313 over molecular weight. So we get it is 4123.5. So and then we could calculate the density by using the ideal gas law. So the perfect gas law. So and then we have the P over RT. The P here is the atmospheric pressure. It is okay for you to use 101 kilopascal. So if you want to be specific, you can use 101350, but it is okay for you to use 101 kilopascal or 101.3 is okay. So and then you substitute the value of atmospheric pressure. So and then because here the question stated as 1 atm. So if the question gives you 1.5 atm, so you need to change the value of this one. So and then the value of R, and then the value of temperature in Kelvin. So we have 0.0838 kilogram per meter cube. So this is the density for the hydrogen. So mean what we have here, the density 0.0838 is actually come from this calculation. Okay, so it's depend on the real calculation. So and then we are going to calculate the value of mu. Okay, because normally we will just remember the kinematic viscosity and then we substitute. But in high level, and start from master and PhD, you need to understand, that certain element, for especially gas, because we are talking about hydrogen here, is very sensitive with temperature and pressure. So if you heat it at certain temperature, so it might be expand, so the viscosity may be different. Okay, now we need to calculate what is the viscosity. Is it same with this one or not? Okay, how to calculate that one is we use the prediction equation of this one. Okay, so it is mu over mu naught equal T over T naught over N. So again, this equation is actually, if you read the textbook, the viscous fluid flow, you will find that the idea is actually comes on the previous researcher do the experimental works and then they do the curve fitting. So and then they could determine that the relation between mu over mu naught is actually have a similar trend with T over T naught with certain value of N. So the value of N is actually given by a table, by a fixed number. It's about the curve fitting from the previous researcher. Okay, so the value of hydrogen is 0.68. So it is actually come from the curve fitting from the experimental work. So we need to remember this term, this value. So and then the T naught is actually 273 Kelvin. It is 0 degrees Celsius, and then this is the standard kinematic viscosity at 0 degrees Celsius. So and then okay, so in your textbook, okay, they will give you equation 135 and 136. Okay, they will give you the value of n here. So again, the value of n is actually come from the curve fitting from the experimental works. So you could get the value from this table, you substitute, and then you could get, because in the question here it gives you the value of 20 degrees Celsius, so means that you could get the value of T here. So you substitute, so you will get it is 8.411, quite different with what we use here, 9.005. Okay, so we have this one. Okay, I'm sorry. Okay, so we have this. Okay, so we have this value. So we substitute into the equation. So we found the Reynolds number is 2,393. So this is the idea of the way we calculate the Reynolds number. Again, not just remembering the equation, you must know the situation and you must know to differentiate between the fluid. If the fluid is affected by the temperature, you need to calculate the value of density and the value of viscosity, very specific, depends on the situation.